Welcome to Lesson 2 of Chapter 5, Caching Strategies. Once you have your data storage sorted, the next major lever for performance is caching. Let's understand why it exists and when you should reach for it. Caching becomes relevant when a piece of information is requested too often and its value will not change, at least not for some meaningful period of time. Historic values are the perfect example. They will never change, so computing or fetching them from a database on every request is pure waste. But even non-historic data can be a good caching candidate. If a value might change but you can tolerate it being a few minutes stale, caching it for that window dramatically reduces database load. Caching is especially valuable when the data requires complex computation or multiple database joins to produce. If the result of a heavy aggregation query can be cached for 5 minutes, you save hundreds of database round trips during that window. In more complex systems, the cache acts as a second level of abstraction between your application and the database. Bidirectional updates are common here. When a user action changes data, you update both the cache and the database simultaneously. This is faster than simply invalidating the cache and forcing a fresh database fetch, because you already know what the new value is. The core cache logic follows a simple flowchart. When a request arrives, ask, is the value already cached? If yes, return it immediately, no database call needed. If no, produce the value, store it in the cache, and return it. This is the cache-aside pattern, and it is the foundation of almost every caching strategy. Now, where do you store the cache? You have 3 main options: in-memory within the process itself for the fastest access on small datasets, on disk when the cache data exceeds available RAM, for example, generated image thumbnails, or in an external service like Memcached or Redis. The external services have the advantage of zero setup overhead to start, and they allow the cache to be shared across multiple application instances, which is critical at scale. Now we need to talk about one of the most painful problems in Node.js caching, asynchronous caching. This is where many developers get tripped up, and the book is very direct about it. The problem won't show up easily during development. You'll only notice it when load is high and you see a flood of identical cache miss requests hitting your database simultaneously. Let's walk through the naive cache pattern first. You maintain a user's object as a hash table. When getUser is called, you check if the user is already in the hash. If so, return it immediately. If not, fetch from the database, store it in the hash, and return it via callback. This looks correct, but it has a critical flaw. Imagine fetching a user takes 10 seconds due to a network hiccup. During that 10 seconds, your function is called 100 times for the same user ID. What happens? Each of those 100 calls checks the hash, finds no entry because the first fetch hasn't completed yet, and fires a separate database query. You now have 100 simultaneous database requests for the same user. This is the thundering herd problem, and it will crush your application. The correct solution is to queue the callbacks. Here is the pattern: the first time a user ID is requested, create an entry in the hash with a queue array containing the callback. Then fire the database fetch. Any subsequent request for the same ID, while the fetch is still in flight, finds the hash entry, sees it does not have a data property yet, and simply pushes its callback onto the queue. When the database finally responds, you store the user data, then iterate over the queue and call every waiting callback with the result. Then delete the queue property. This pattern ensures exactly one database query per user ID, no matter how many concurrent requests arrive during the fetch window. It is elegant but counterintuitive, and it is a perfect example of why the book says, it is not the paradigm that has pitfalls, it is the way. Node.js forces you to think asynchronously, and your caching logic must reflect that discipline. Let's round out our caching knowledge by looking at the 2 most popular external caching services, Redis and Memcached, and also address the ORM trade-off that the book raises in this context. Memcached is a simple, distributed memory object caching system. It is extremely fast and easy to deploy, with essentially zero configuration to start using. It excels at simple key/value storage with automatic eviction. The limitation is that it only supports strings, and it does not natively support persistence or complex data structures. Redis goes much further. It supports a rich set of data structures, strings, hashes, lists, sets, sorted sets, and more. It supports transactions, time-to-live keys with automatic expiration, pub/sub messaging, and optional persistence. This makes Redis an excellent choice not just for caching but also for session storage, rate limiting, leaderboards, and real-time data pipelines. Both services need zero setup to begin using and can be shared across multiple application instances. Now, there is also an intermediate approach the book mentions. Services like ZeroMQ and RabbitMQ can act as proxies in front of your data storage servers. They create the illusion of a single unified storage server and maintain constant throughput even as your dataset grows. In small scenarios this is overkill, but in large distributed systems, adding a message queue layer between your application and storage can smooth out burst traffic effectively, Finally, let's address ORMs, object relational mappers. ORMs were designed to give you a database agnostic layer and let you model your business entities directly in code. For standard CRUD operations on moderate datasets, they are valuable. However, for large datasets or historic data, they come at a real cost. Each ORM entity typically carries extra memory overhead, and the query abstraction can prevent you from using database-specific optimizations. The book's guidance: use ORMs pragmatically for standard operations, but be willing to drop down to raw queries for performance-critical paths, especially when dealing with tables that hold gigabytes of data.